All right. So remember our chapter is related to work and energy.
Yeah.
So we're going to be doing work energy theorem probably to solve this. There could be some kinematics, but let's see if we're able to just do it with work and energy. So there is a block here, mass 1 kg, it's released from rest. The angle of the incline is 30 degrees. 2 meters above, along the incline, a spring with a spring constant of 500 newtons per meter. So we know this displacement of the block. We know that's wrong, right? Like it's 500.
Yeah.
Interesting.
Said
So it,
125.
yeah,
Okay,
I
that's confusing, but the question says it's
500.
500.
Let's go with that. Yeah, let's go with the 500. We'll see if our answer matches. If it doesn't match, then we'll try the other K.
Yeah.
Coefficient of friction is given, so mu is given to us. It's kinetic. The block slides down and compresses the spring. Okay. Um, First of all, what is going to cause the block to slide down the inclined plane?
Slide down. If
Yeah,
like,
it's this component of gravity, right?
yeah. I was like, if gravity is like greater than
Friction.
the other component. Yeah.
Yeah, if it's greater than friction. Um, okay. First one says find the speed of the block just as it makes the first contact with the spring. So just as it reaches this point right here, right? Okay. What concepts can we use? We want to find um, the speed. So kind of think about kinetic energy, right? Like if you could just convert the amount of work done for the box to move from here to here, that amount of work done should be equal to its kinetic energy, and then kinetic energy is half mv squared, so we can easily find v from there. Does
Right.
that, yeah, does that logic make sense?
Well, you're using the energy to find the speed.
Yes. So it's kind of like if we can find the work done by the block to move 2 meters down the incline, then according to work energy theorem, that work should be equal to the change in its kinetic energy. But let's say initially the box was like we didn't have a velocity, it was just released from rest. So that should be equal to its kinetic energy
Yeah.
when it makes the contact with the spring. And then we can use that kinetic energy equals half mv squared to find the speed. Right? Are we good with that logic?
Yeah. Yeah.
Okay. So
Yeah.
the
Well,
important thing
V is
now,
in the EK equation, anyways.
yes, exactly. That is correct.
But you have to find
So
EK
now
first
the
to
most
be able
important thing for
to.
us to do is find work, right?
Yeah.
So the question is, how do you find work?
Well, work is
Mm.
distance times.
Force times distance times cos theta.
Yeah. In this case, it would be cos 30, right?
Yeah. So the force that we're working with here is just F cos 30 already. Oh, no, no, sorry, that's my bad. The force that we're working with is mg sine theta, because this is the component that is
Oh,
going with the
yeah.
direction. Now we have to be careful here. This is the component of the gravity that is going in the inclined plane, right?
Yeah.
What is the direction of motion? This way. Yes?
So friction is the other way.
Friction is the other way. But right now I'm talking, yeah. Let's do F net. This has to be F net, by the way. Direction of motion is this way. Mg sine theta is this way. Friction is this way. Where is F net? Because it's sliding down, gravity should dominate.
Right.
So F net should also be acting down because the object is moving down. Now the question is, what is the angle between the direction of displacement and the direction of force? What is the angle between force and displacement? Are they parallel, perpendicular, at some angle?
Sorry. My parents were talking in the background.
Oh, no problem.
The angle between 180?
The
No, they're
angle, but
parallel.
they're parallel, same direction. So
Yeah. The angle is 0.
0,
Yeah.
which means cos theta is equal to cos 0, which is equal to 1.
Yeah.
So work done is basically just going to be your F net times displacement. See, it's tricky. Why it's tricky? Because this 30 degrees make you think that you have to put the 30 degrees somewhere.
But it's not.
It
You
will,
don't use it.
you won't use it for this formula. You won't put it here because this angle is specifically for the angle between the direction of displacement and direction of force. You will use it, however, if you when you do, your components of gravity, you have mg sine theta, you can put 30 there, but you will not use it in this formula, okay? Now this is
Yeah.
the equation. Let's find F net. So we said F net is equal to mg sine theta minus force of friction. What is the formula for force of friction? What should I write there?
Force of friction is U Fn,
Yeah.
and then,
What is
well,
Fn?
it depends. Sine mg.
Sine mg?
No, force of friction is, you have to use the angle sometimes for force of friction, right?
For Fn, actually. What is Fn?
Oh,
Right?
mg.
If we draw a free body diagram here, this component is mg cos theta. This
Yeah.
component is Fn. If we do the sum of forces in the y direction, like if we quietly do this here, sum of forces in the y
It's
direction should be
mg
0. Yeah, Fn comes out to be equal to mg cos theta.
Yeah.
So this is going to be mg cos theta. Are we good?
Yeah.
Okay, great. So what are we going to do? We're going to combine these. Let's see, plug things in and see what we get. So mg sine theta minus mu mg cos theta. Just plugging the numbers in now. 1,
Mm.
9.8, and 30 minus mu, which was 0.2, I think. 1, 9.81, then cos 30. Let's see. Okay, I get 3.205. 2058, so let's just say 3.206, just keeping a few extra decimals. And
Right.
then to find work, what are we going to do? We're just going to multiply this F with the
The
displacement of just
distance.
2 meters.
Yeah.
Yes. So let's do 3 point this and then multiply this by 2. So 6.41, let's say, joules.
Yeah.
Good. Perfect. And then once you know work, we can use work energy theorem. The work energy theorem is work is equal to change in kinetic energy. We're going to assume that the initial kinetic energy is just 0. Why? Because we can assume that velocity initially was 0. Because the blocks, we didn't push it with any velocity. It was just there, and then we just released it and started sliding down. So initial velocity was 0. So it's kind of like EKF final minus EK initial. Initial is just 0. We're assuming it to be 0. So work done is equal to half m v squared, which was the velocity with which it will hit the spring. Okay. Are we good so far?
Right. Yeah.
And then we just basically use this, or you can just isolate v variable. So multiply by 2 on both sides, divide by m on both sides. That's v squared. To get rid of the square, just take a square root. So
Yeah.
that's it. Let's plug our numbers in and see what we get. So square root of 2 times the work,
Which is 6.421, right? 412.
6.412. And then we divide it by the mass, which is just 1. So that is 3.58
Uh,
meters per second. Let's check if that was the right answer. Yes, that was correct. 3.58 meters per second. Good. Look at the question one more time. Are you able to follow through the steps we just did?
it's 2W squared, 2W over mass and the root of that, right?
Correct, yes.
The 2 times 4.1,
6.41.
wait, 2 times 6.41, right?
Yes.
Oh, so then you take the root of that. Okay, yeah, I got the same thing.
Perfect.
Yeah,
Amazing. Good. Are you okay with the steps we just did in terms of finding work and FNet and then putting it equal to half mv squared? Understand that?
yeah, yeah,
Great. Okay. Good. So part one's done. Part B, if the mass compresses the spring by a length x. So obviously the mass has now hit the spring and it's going to compress it a little bit because of all the energy it is carrying. And let's
yeah.
say it compresses it x. Um, find an expression for the total work done on the block since its release in terms of x. Total work done on the block since its release in terms of x. So since its release all the way until it compresses the spring and stops. So what is the work done as it compresses the spring? What is the work done of the spring? Do we remember? Do you remember the
The work done
formula?
of the spring
Hmm.
is spring constant times distance, right?
Spring constant time. Yeah. Uh, that's force. If you want to add
Oh, right,
the work, it's half kx squared. That's
right.
work or energy, right? Okay. Um, okay, so that is going to be the work done as it compresses the spring a little bit. So half kx squared. Now, the other work done, now since its release, it has been traveling down all the way.
Yeah,
And when we did this part of the question, part A, we were just stopping, let's say, we just make it a little less crowded here. For part A, we were kind of just stopped here because it was like makes the first contact with the spring. So we stopped there and we did work done to that point. Now, let's say the spring is compressed and maybe it compresses all the way and now it stops here. So due to this, we already found the work done by the spring, but that's just the spring. The force of gravity is still and friction are still gonna continue working until it completely comes to a stop, right? And
Yeah.
so we gotta um, figure out that this x centimeters or meters, what is it? Let's just say x meters. Um, the total work done by the box since it's released all the way it comes down to x, okay? And for that, we're going to continue this exact same thing. For example, the force is going to be this exact same force, but the distance now is going to be 2 plus x because of this little extra x distance it also travels, right?
Yeah.
So total work done is going to be um, like this whole thing, like we can continue writing this whole thing, but just we're gonna multiply it by the distance d, which is 2 plus x this time. Do we understand that?
Yeah.
Okay. So total work done. Um,
Total work done will be like that plus.
the the you could say the work done as it work done on the no, work done by the force of gravity. Yes, let's
Yeah.
just put it that way. So work done by gravity. So that work is done this way. Minus work done by the friction. Yes.
Yeah.
What about the work done by spring? Would it be added or subtracted? Added or subtracted?
Um.
Think about the direction in which spring is acting on the block, right? Friction is going, gravity is going this way, and FG sine theta. Friction is going this way.
Yeah.
Where is spring
And
gonna act?
spring away from the
Yeah,
block.
this way, right? Because spring is
Yeah.
wanna, the box compresses, the spring is gonna wanna,
Yeah.
move it away. So
Yeah.
subtract also this work of the spring. Good.
Right. Yeah.
So work of gravity is basically just mg sine theta. And what is the distance now? 2 plus x.
Right.
Work of friction is mu mg cos theta. What is the distance? 2 plus x. Okay. Springs work half k x squared. That is
Mhm.
equal to work. This is it. You can plug the numbers in, but we don't know x, and they want us to find the work in terms of x only. So
Mhm.
you can plug the
So
numbers
then you
that
could
you know.
just like, but
Yeah,
then you could just expand the formula, right? Like two. Oh wait, no, because it's multiplying.
it would be better to just plug the numbers in because you know the value of all of this, right?
Right. Okay.
So it'll be easier if you just plug the numbers in and try to like find a numerical number and then multiply that with 2 plus x. Then you can expand. Yeah.
Yeah.
Okay. But yeah, that part's easy. That's algebra. So I'm going to leave that to you. But
Yeah.
this is the important equation that we found. And then
You
part
have
C,
to do like
yeah.
and like weight gravity like subtract because you should write that first because it's like the largest component, and then you subtract the others,
Yeah.
right?
It's about direction as well. Um, yeah. So because it's sliding down, so I usually just take the force that is going in the direction of motion to be like my positive force. And anything opposing that, I usually take it as negative because if the object is going down, it means that that force is obviously dominating all other forces. So
Mhm.
it with questioned, it makes sense to put it positive because then my answer would have positive signs. This doesn't mean that if you do the other way, like if you did your force of friction and energy of the spring, if you take that to be positive, your magnitude would still be the same. Your signs would be flipped. So,
Mhm.
um, as a good rule of thumb, I like to keep the force that is moving in the direction of motion to be the positive force because that's going to dominate the entire motion.
Okay.
Yeah, that's the only reason. Okay, good. Let's do maximum compression of the spring. So maximum compression of the spring could be whatever. Let's just say it's X because we don't really know what the maximum compression is. But let's understand what happens at the maximal compression.
You're finding X?
Yes, we're finding X. What happens at maximal compression? And by that, let's say what happens to the speed.
Well, turns out it's so like first, like the object is on the spring and then it coils and then at max, like the object moves away from the spring faster.
Yes, but let's just stop the time when it compresses it to the max momentarily. Okay.
Mhm.
It's kind of like I throw the ball up and I'm going to stop the time at max height. What happens at max height?
Oh, like the acceleration is zero, or
Velocity
like
is zero.
velocity zero. Yeah.
Velocity is zero. That's always what happens when any object changes direction of motion, like 180 degree. So for you, the object momentarily stops and then changes the direction the other way. And the same thing happens here. So when it reaches maximal compression, this way it goes, and then maximum compression kind of momentarily stops, and then
Mhm.
spring bounces back and releases it at a speed and then goes away, right? So at maximum speed, sorry, and maximum compression, velocity is actually zero because we say that it momentarily stops. Okay, that's
Right.
why. So
But maximal compression in the formula is what the X squared is, right?
no, this could be this could
Or
be
it's
whichever
everything from K.
compression. It could be
Oh,
somewhere in between. Like it could have been like this, and X could represent that. It's just the work done would be less than. Max work done is when your compression is max, right? But it doesn't mean that X is always maximum. It could be somewhere in between here as well, like somewhere maybe um like somewhere here, just like this little distance, that could be X. But if you put
okay.
that X, then you get little work done, right? Because work done would be little. But it just means that is the work done by that compression. Max work is done by max compression. Does that make sense?
Yeah.
Okay, good. So we're gonna work with the fact that final velocity becomes zero, um, change in kinetic energy would be zero. Because if you
Oh, velocity zero.
yeah, we said that it starts at zero, so initial velocity would be zero, final velocity would also be zero, so change in kinetic energy would be zero, which means work done, the total work
Equals
done.
zero?
Yes, work total should go to zero, which means the work done by the gravity to push it has now been balanced by the work done by spring and friction. So the
Mhm.
positive equals negative and then should become zero altogether,
Right.
which
So you
means,
have work gravity minus work friction minus work spring equals zero.
correct. And we already have that equation right here. So you can say
Yeah.
work of gravity. I'm going to put the numbers in now. So
I'll start plugging them in.
yeah, we just basically have to solve for x. We can put this entire equation equal to zero. That's the premise. Okay,
Yep.
great.
But the 2 plus x stems from the fact that it's the distance plus x, right? Like
Yeah,
2 plus the
because
rest
now
of the distance.
it's moving beyond the 2, so we have to account for the entire distance.
Yeah.
Put all that equal to 0. Let's see what that
Then
is.
you would have 4.905 times 2, 9.81 plus 4.905x.
Are you solving the bracket itself, or are you just solving the other part, like the front of
Well, I
the?
was saying like 4.905 times 2 plus x is
Okay.
9.81 plus 4.905x.
Okay. Yeah, makes sense. Oh, actually, this is not 0.1. This is just 1.
Yeah, so the mass is 1, right?
Yeah.
I did not get that. 0.2 times 1 times. Oh, I forgot. 9.81
Oh,
plus 30. Okay, yeah.
yeah. Okay. Perfect.
I had to be
Um.
careful with remembering to add gravity and see,
Yeah.
like mu mg.
Mhm. You're gonna. I think. Yeah. Oh, 4.
Well, you'd have minus 6.412 on the other side
Minus 6 point.
because I did 9.81 minus 3.398, and then that's 6.412. But then you move it to
Oh,
the other side, so you get negative 6 point, like equals negative 6.412.
oh, you move it to this side. Why would
Yeah.
you do that? I mean, you can,
Well,
but this could be a quadratic
or you
equation,
just
right?
do, yeah,
So you can just do, you can use quadratic formula, or we can just plot it on I don't know. You could use quadratic formula actually, and then we can just solve it based on that.
right.
Or you,
Okay.
yeah, I would use quadratic formula here and solve it. And um, you can use quadratic formula. I'm gonna put this in Desmos the equation, and we're gonna see what are the x-intercepts that we're getting. So negative 250x squared, was it, what did I have? Negative 250x squared plus, I forgot what I had. I think it was plus 3.20 something. And then plus 6.412 it said. That's so weird.
So weird.
Yeah, it seems like, okay, let's see. Why, I think
I'm doing quadratic formula right now, so
okay, this one's, I'm gonna just copy paste and refresh the page. Let's refresh it.
you got 0.16684.
0.16684. That seems reasonable. I think that was the answer. Could
Because
you
x
repeat?
equals negative point. There were two options for quadratic, so
Yeah,
I ignore the negative one.
yeah, 0.1668, right? And then the negative
Yeah.
one. We will not use the negative one, so it makes sense for us to have the positive solution. So 0.1668. that one.
Yeah, but if we wanted to round to
Centimeters. 6, 8 meters. So that's about 16.7 centimeters. So let's
yeah.
see. That is absolutely correct. Okay, awesome. Okay, that is perfect. Let me stop recording. Okay.